Hello everyone and welcome to this new video where we discuss mathematics and physics on the board. In this video, I'm actually continuing a previous video I've made where I was talking about the beauty of the algebraic or a sort of purely algebraic formulation of Hamiltonian mechanics, where essentially we try to avoid rather using differentiation or partial differentiation with respect to phase-space coordinates and instead try to focus on the algebra. Uh, Now, it turns out that there are some improvable aspects about this particular strategy that I'm going to present today by continuing the example we've seen in the previous video. Right, okay, so let's try to have a quick look at this reminder here. So in Hamiltonian mechanics, you actually provide a Hamiltonian, which essentially characterizes or drives the dynamics, the time variation and time evolution of your system. Okay. Um, Now, just for simplicity, I'm using x and p here, but of course you could do that with generalized coordinates q and p, but also with an arbitrary number of coordinates as well. But here, this is again to put things like much more simply, and also that the video is not too long and cumbersome. So if you've got this Hamiltonian, then from an algebraic perspective, the equations of motion actually look like this. So x dot, the time derivative of x with respect to t, to time, is equal to the Poisson bracket of x with h, and likewise, the time derivative of p becomes the Poisson bracket of p with h. Okay, so that's kind of fairly standard. But the point is basically to solve these things, so to find the equations of motion without having to perform, let's say, the partial differential form of this Poisson bracket. And instead, we just provide these particular algebraic relations, so that xp is equal to 1 and that xx and pp are equal to 0. And if you actually use this only, then you end up essentially by introducing, so that's a necessary step to use this particular algebra, you need to tell somehow that this Poisson bracket can be written in that form. And the triangle operator here essentially is obviously not necessarily like partial derivatives, etc. It's not necessarily characterizing that. However, for whatever Poisson bracket we're looking at, this thing has to provide, the difference has to provide the actual value of that Poisson bracket. So what I'm saying is that this triangle operator is a sort of product that does not necessarily translate into taking partial derivatives. However, that has to be, retrieving back any of the properties we would find had we used differentiation and so on. Okay, so that's kind of what we want to impose to that particular operator. The reason why it can take that form, or at least that's a possible form indeed, is because these Poisson brackets, one of the properties that I didn't mention here is that it has to be anti-symmetric upon permutation. And that's one way to obtain that, is to have this form here. Okay, so with this in mind, then we actually derived, and I'm going to come back to some of the caveats of that derivations, we actually derived that x dot is equal to p over m. Okay, and again, we didn't take any differentiation in this particular treatment. Now, let's have a look at a couple of warnings and things that were kind of slightly incorrect in the previous video. So, some warnings. So, to be honest, the biggest one is that, and in fact, that's I thank very much the person who mentioned this as well in the comment section. I was precisely trying to improve that aspect. Is that we made the claim that we could go from x squared to x x triangle x. Okay. And in fact, this is an unwarranted step. In principle, you say, well, that's fine because xx is 0. So I can, in principle, do that. But then there is a dimensional problem which I actually completely skipped in this particular previous video. And so this dimensional problem is well illustrated here. Xp is going to be equal to 1. So what that means is that essentially the dimension of my triangle operator needs to be 1 over the dimensions of the product of x and p. Okay, as it turns out, the product of x and p has a dimension of an action. Okay, and so basically you can't necessarily translate into that. So if you just convert like this, there is a dimensional problem. So instead, what we are going to prescribe, so we are going to propose the prescription that if I want to convert from a product and like a simple product between commuting quantities, so that wouldn't work for x and p, for example. But if I want to convert that into a product, so for example, I would have x squared is going to be yes equal to x. That's fine to write this, but then for dimensional reason, I need to multiply it by some quantity S0, S for action, and S0 for some kind of reference action. And so x squared is equal to some action of reference and then x and then delta x. So this is going to capture the commutativity anyway of the product, and then it takes care of the dimension aspect as well. Okay, so I'm assuming that I can convert a product between two commuting quantities to be expressed with this delta or triangle operator, but then I need to put in some sort of dimensionally some dimensional factor there that is just going to play the purpose of making sure that things work fine. Likewise, you can imagine something like x being equal to S0 x and then triangle 1, for example. Okay, that's also something that we are going to assume. And again, I want to insist here, because that's obvious from looking at it, that the triangle operator is not the same as the differential operator that appears in the differential representation of the Poisson brackets. It can't be, okay, otherwise you would get x triangle 1 is 0. So it can't be the same. But it plays the same role insofar as Poisson brackets are concerned. Okay, that's the idea. So if we assume this kind of thing to be true, then we can move on to find out, therefore, P dot is equal to, and that's a Poisson bracket of P with H. And so that's going to be the Poisson bracket of P with P squared over 2m plus the Poisson bracket of P half K x squared. Now, from this equality here, P equals 0, then we're also going to get that P squared equals 0. And one way to actually get that is simply by saying that P squared is equal to S0 P triangle P, and then we can kind of retrieve various things there as well. So the thing here is that this thing is going to be equal to 0. And so what therefore I need to do is continue here with this one. And so that's going to be half K, and then we are going to have P triangle x squared, and then minus half K, and then x squared triangle P. So again, that's an operation, that's an operator, triangle, a binary operator. This is not a delta, to mention that this is a variation in P, okay, so just be careful notation-wise. And so now what I'm going to do is write that x squared is equal to S0 x triangle x, okay? So that's going to be equal to half and then K p triangle x squared, and then minus half k S0 x triangle p. Okay, now I'm just going to put here one thing that is important, is that from this equality I've got that x triangle p minus p triangle x is equal to 1, and so that gives us that x triangle p is equal to 1 plus p triangle x. So what I can do here is replace the x triangle p by 1 plus p triangle x. So I'm getting half k and then p triangle x squared minus, and so half k S0, and then we have x triangle, and then we've got 1 plus p triangle x. Okay, so then when I expand, I'm going to get, by using this particular operation as well, we are going to get that this is half k p triangle x squared, and then minus half k x, and then minus as well half k S0 x, and then p x. Okay, so now what I do is that I substitute, basically here I've got x triangle p, which I replace again by this one. So I'm getting half k p triangle x squared, then minus half k x, and then minus half k S0, and now I've got here 1 plus p delta x, and then that is delta x here. This is actually going to give us the following: half k p delta x squared, then minus half k p delta x squared, and then minus k x. And so all in all, what we end up with is that p dot is equal to minus kx. And if you just wonder what happened between here and there, S0 1 triangle x is equal to x, and then we've got S0, where are we? P triangle x is basically equal to what I've put here. Okay, that's this S0 is going to basically give an x squared for this. Okay, so here again, the trick was that what are the conditions to go from a simple product between commuting observables in the sense of Poisson brackets, and then the way we actually do that is via the triangle operator, because again it's commuting with respect to this operator, but at the same time we need to introduce a dimensional quantity here that has a dimension of an action and make sure that kind of everything is kind of watertight when it comes to physical dimensions. And you know, at the end of the day, we still end up with this particular result here. And so if you actually put together this equation and the one we had found before, which is this one, then you can solve the equation of motions for your system. Okay, so I think now this is basically fairly workable, and so you could work out any kind of equation of motion, whatever the functional form of what you're looking at of the Hamiltonian, and you would actually get somewhere. Usually the kinetic part anyway is quadratic in the momentum, and then what could change, of course, is the potential part, But then in the worst case scenario, you can get there by simply providing a sort of Taylor expansion, Taylor series expansion of your potential, and basically get there as well. So on that note, basically, I think this shows how this works, and I think that would be great if you try to have a go. Of course, some of you who have already done some quantum mechanics, you may see where the connection lies here, and this is something we are going to see in later videos as well.